So welcome to this lecture on new trends in polynomial homotopy continuation. So I thank the organizers of the mini symposium. So obviously the title of my talk is inspired on the title of the mini symposium, but I have a subtitle to give the talk some focus. As the outline shows, I will get into the trends in polynomial homotopy continuation after my explanation what I mean by a priori step size control. But first I will spend some time explaining the problem. So what is our problem? So we want to solve polynomial systems with homotopy continuation methods. We do have generically optimal homotopies for systems with a linear product structure, and we can solve sparse polynomial systems also equally well if we exploit the Newton polytopes. And for Schubert problems, we do have Littlewood-Richardson homotopies. So the assumption that we have no singularities on the paths and that we do not encounter diverging paths is quite reasonable when we assume that we are in the context of generically optimal homotopies. So this talk is not on homotopy methods, how you should construct a good homotopy, but is on tracking the solution paths defined by the homotopy, paths that are originating at known solutions and that are ending to the solutions of the system that you want to solve. So we want to determine the step size of the path tracker, keeping in mind that we do not want to keep our step size too small because then we have to take too many steps. And we also certainly do not want to lose any of the paths, which could happen if we set our step size too large. So my next slide is a cartoon kind of to warm me up for the problem. So we have a path drawn in red that we want to approximate. So the path itself is continuous, but we will discretize this problem computing points on the path. And you can see this is done with a variable step size, and we follow the directions of the tangent vectors. Sometimes it goes very well, so going from x0 to x1, actually it went well. We enlarged the step size a little bit, but then actually we got farther away from x2, but when we went from x2 to x3, the went all very smooth, and then we enlarged the step size again. So you can kind of see what the problem could be if you only take into account the past performance of the corrector, essentially. If you take the past performance of your predictor as the guideline to set the next step. So if you have never seen path tracking, so then with knowledge from calculus, this is a good way to get into it. All right, so this is a talk that describes materials from 3 different papers. So the central paper on this slide, it has its focus on step size control, but power series and parallel algorithms are actually what I would describe within the setting of the trends. Power series and parallel algorithms are 2 very important trends in polynomial homotopy continuation. All right, here another limitation or definition if you want. So what I mean by numerical continuation is that we apply adaptive step size control in predictor corrector method executed with double precision arithmetic. So we are in the context of numerical analysis. So there are at least three very valid alternatives to numerical continuation. One can equally adjust step sizes quite well with interval arithmetic, or more recently and more general, perhaps ball arithmetic. There are symbolic deformation methods. And then last and probably certainly not least, there are certified tracking methods, for which I also list here two references. So these are some of the alternatives. There are maybe more, and I may also not have listed all the relevant, may not even have, so the papers that I list here are some of the samples in the literature. So what is important on this slide that I want to emphasize is that we deal within the setting of numerical analysis. I actually learned from Padé approximations by reading papers in symbolic path tracking, but Padé approximants have been used as predictors for more than 30 years already. So the first reference here mentions it. Of more recent nature is the consideration of the poles of the Padé approximants. So that is done in the holomorphic embedding load flow method, a method that was published in the IEEE electrical engineering literature. So what the holomorphic embedding load flow method does, it actually constructs Padé approximants and then looks at the roots of the Padé approximants to determine the step size control. All right, a little bit now more trying to define what I mean by a priori step size control. And I will do this by contrasting with a posteriori step size control. Kind of now trying to see the first cartoon slide in another light, a little bit more practical perhaps. So we have a predictor corrector method. The predictor predicts the next point on the path, and the corrector corrects it. The corrector is typically Newton's method. For the predictor, you can use Padé approximants. And you can see there are two feedback loops here. You do not go into the corrector stage if the predictor gives you a residual that is way too high. And also you actually will cut back the step size if the result from the corrector gives you a residual that is too large. But by the way, if you think about making your own path tracker, one common mistake that novices typically make is to allow too many corrector steps. So this is how the feedback control loops work in an a posteriori step size control. So feedback control, the proper engineering term for trial and error. It works very well if it is properly tuned. So there is in essence nothing. So a posteriori step size control has served us very well for a very long time. But what I would like to introduce now is actually a priori step size control. And a priori is now actually defined negatively what it is not. So but you do actually not rely on feedback loop, except in the case for verification. So the checks are still there. Verification is important. Here is another cartoon, and trying to define and introducing the more positive definitions of what I would like to introduce as a priori step size control. So if you think about following a path, then what could be the problems? What could cause you to lose one path? Well, one cause is the high curvature. So you take the tangent line, but the path actually curves rather in a very strange way, and your tangent actually leads you off to another path. Then the other obvious cause is the nearby singularities, and that is actually happening when the curves are close to each other. So the cartoon here is stating these causes as two separate ones. So I made the point for curves that are close to each other to actually make them rather flat, and for curves with high curvature that they are far apart. But of course, in practice, if you have one problem, you have another one. So the problems are usually always coming. Typically, things are not as clear-cut as on this cartoon. So this is my introduction to the problem of tracking paths. So if you have an a posteriori step size control, you can't really deal very well with these two cases of high curvature and paths that are close to each other. All of a sudden, the paths start to close, or all of a sudden, the paths become very close to each other. It's very difficult to anticipate that within a posteriori step size control. All right. I mentioned the poles of the Padé approximants already. Here is an old theorem, the ratio theorem of Fabry, that tells you that you can predict nearby singularities by looking at the ratio of the coefficients of the Taylor series developments of the curves. So why Taylor series? Well, we are at regular points, no singularities. So we assume that the Taylor series is unique and well defined. So then also this ratio is actually well defined. And actually, the theorem itself is not that hard to see why that could be true. Is that if you look into the Padé approximants with linear denominator, then the pole where it actually is, where you can't use that Padé approximant, that pole is actually showing up. That pole will be equal to the ratio. So where the Padé approximant is not defined, obviously when there is a nearby solution at infinity, but actually what Fabry says, it also is more general. So solutions at infinity and singular solutions in this context, they are equally difficult to treat. All right, so we compute Taylor series, and how do we do this? Well, you can genetically, so in general, you can, working with power series is quite neat. Power series are like polynomials, except that you can invert them. So you can work with power series just as they are numbers. But if you do so, it's actually not really that efficient. So the really good way to deal with power series, running Newton's method with power series, is actually to linearize the problem, and to, instead of working with a matrix of power series, you work with a power series where the coefficients are matrices. This has the immediate consequence that all the good linear algebra that you know is immediately and you also have a sharp cost estimate. So there is overhead. So there are some extra systems, linear systems to solve, but it remains essentially a cubic in the dimension. The other issue is that if you are concerned, as we are in numerical analysis, with accuracy, so that's perhaps even the prime concern, is that you can see that if you are losing 2 decimal places in every step here of the series, that after 8 steps you may have lost 16 decimal places in your power series. So we have done an error analysis. So the 3 lines here do actually kind of injustice to this analysis, but this actually is somehow some caution. And I'm actually also now introducing what I see another trend, multiple double precision arithmetic. All right, and I now arrived at the most technical slide in my talk. So there is the curvature that also is a concern. And to estimate the curvature, we're going to compute a series truncated after the second degree. So the Hessians of the polynomials come in. With linear algebra transformations, we can derive a bound on the distance for the nearest path. That lower bound involves the singular values of the Jacobian matrix, the smallest singular value of the Jacobian matrix, and all the largest singular values of the Hessians. So with that lower bound, one can compute another error estimates in combinations with the Padé approximants. So that's that error E0 that appears here, where we have some power of the delta t, our step size, that is determined by the degrees of which Padé approximants we are using. So there is way more to it in the derivation, but this is a summary slide on how we can estimate the distance to the nearest path, taking into account the curvature. The more the paths are going to curve, we're going to see this in the Hessians. And you can see the information of the Hessians occurs in the denominator of that path. Here is a schematic summary to indicate that what is important in what are the important computations in path tracking algorithms. So this is the algorithmic differentiation and the linear algebra. So linear algebra occurs is essentially at three of these blocks here. We solve the block Toeplitz, the lower triangular block Toeplitz, when we run Newton's method on power series. We also solve linear systems in the Padé approximants, and then also we do linear algebra when we compute respectively the smallest singular value and the largest singular value. So there's just 2 bounds, a bound on the curvature, and then also this an estimates on the. So if we are having an estimate on how the need weight beta factor, and equally we have actually a safety factor for the distance to the nearest path. So that was that eta, and then we multiply this with another tolerance. It could be used as a potential of what we actually mean by a priori step size control. So then there's a lot of work that we have to do. So let's try to quantify this a little bit. We have the singular value decompositions of all the Hessians. The Hessians themselves can be computed efficiently directly from the Jacobians in cost overhead factor that is linear in the dimension. If we assume that we are using power series truncated at the same degree as the dimension, then actually we have the n log n factor coming in. Now, you could mitigate that a little bit and saying that in general, our number of equations and number of variables will be larger than the degree of our power series. So then the cost overhead factor would be n. Quite substantial. So system with 20 equations, 20 variables it's gonna take 20 times longer. But I want to motivate the other trend in polynomial homotopy continuation, and that is parallel algorithms. All right, so this was actually the main part of the presentation on a priori step size control, which I will just conclude with some computational results. So the a priori step size control is already in use for more than 2 years now. So we tested this on large systems because it's not only important that it works, that, hey, we can predict the step size, but also that it actually can do substantially large instances. And in particular, so here the first instance is a well-known benchmark. So the benchmark itself comes from the POSO, from the POSO project 20 years ago. Known benchmark also in computer algebra. What is important, we can compare with another very important implementation where the authors actually computed 4 path jumpings in their runs. So this is another indication that with a posteriori step size control, it's very difficult to have everything always right for a large number of paths. So another example involved cubic equations, which was actually more nonlinear. So the runs with Katsura, here the condition numbers start to be large. So I would state that for Katsura, it might be the last case where you can get away with double precision. For higher case, you actually may need double precision. Although are very important. All right, now go to talk to say something about parallel. Message passing was used in the previous slide. Here we are using shared memory computers to actually derive approximant algorithms. So a back substitution looks very sequential, but given the right sizes, pipeline is actually extremely efficient. So actually you get a speed up ratio that with the number of degree D threads, the speed up tends to be close to 1/4 of D. So this is the one of the trends, the shared memory. And then there is the trend where I'm actually most excited about, but I did not want to focus my talk entirely on GPU computing. What you see in this summary table is a sequence of GPUs. So the oldest GPU is more than 10 years old. The most recent GPU was purchased 2 years ago, the Volta GPU. And in 10 years, you could see that GPUs have increased about 20-fold in speed. So the processor speed is kind of stuck at gigahertz, but combined, so gigahertz means that you can do about 1 billion operations per second if everything is coded up well. With graphics cards, you can do 1 trillion computations per second. So 1,000. So I'm still working the GPU implementation of the path tracker. This is one experiment on how you evaluate polynomials efficiently at power series at very high degrees and at a tenfold increase of the precision. So for that, I used the software that was generated by Campari. This kind of is a snapshot of a talk I presented at an earlier conference in. Then the last trend are power series. So throughout this project, I spent a whole lot of time thinking about how to work with power series efficiently. And you can actually say that power series are not at all a new trend, even not in homotopy continuation. So earlier in the introduction, I mentioned homotopies exploiting power Newton polytopes, while power series were already occurring there. So power series and homotopies, that's an old trend, at least 25 years old, and if not longer. But now that we have more explicit tools to work with power series, you can actually do experiments like done here. You can take a polynomial system that has as input power series. And how do you get power series? Well, you have a sine or a cosine sitting in there. So many of the interesting problems that derive from mechanism design actually are formulated with sines and cosines in it. But now actually we can think about these problems more directly and perhaps more efficiently in terms of power series. There's always, of course, a catch. So if you are here in this experiment, and this can already be done with BHCPAC, so if you flip actually the sines with the cosines, then actually you need Laurent systems, Laurent series, and that's actually the really newer trend where I would like to go into. All right, my time is about up. So I mentioned one important trend in polynomial homotopy evaluation, the use of a priori control, which actually gives a cost overhead for which we use parallel algorithms. Parallel algorithms used to offset cost in multiple double arithmetic. And then more in the future, one can think of expanding, so polynomials are also power series, to actually expanding the input to more general systems. So the most important link is that I mentioned papers, but the papers, just as this talk, is kind of a very vague summary and kind of an introduction to the papers. Papers themselves are also kind of, there's still one very large important thing, and that is the software. So if you like, you can eventually, after this talk, immediately go into the software. So my time is about up, and I will stop here. Thank you for your interest in